Good morning, friends. I'm Suneeta Phadkule, working as a professor in mechanical engineering at JSPM's Jaywantrao Sawan College of Engineering, Hadapsar, Pune. This is our video lecture number 24 on unit number 3, that is 2 DOF system undamped vibrations. Today we are going to learn or we are going to solve problem 1, that is one problem only on longitudinal vibrations. So what is the learning outcome? Learner, that is you will be able to estimate two natural frequencies and two principal mode shapes of 2 DOF longitudinal vibrations. So this is your syllabus content. Okay, so free vibration of spring couple system, longitudinal vibrations we are going to study. Let us see the recap what we have learned in earlier lecture. So we have seen that there is a typical procedure to solve any problem of 2 DOF system, whether it is longitudinal vibrations or torsional vibrations. Same procedure should be used. And believe friends, this is a very typical procedure. If you understand this procedure, you will be able to solve any 2 DOF problem. So let us have a look on this one. So what is the first step? First you draw the free body diagram in displaced configuration. And you have to assume either x1 is greater than x2 or x2 is greater than x1, and accordingly you have to show the direction of coupled spring force for both the masses. Okay, so according to that, which one is greater, your direction of spring force, middle spring force, coupled spring, which is the intermediate spring, its direction will be changed. Second step is write down two equations of motions by applying D'Alembert's principle or Newton's second law of motion. You know it, all the details you have already seen it in unit number 1. Okay, then step number 3, simplify equations by collecting similar coefficient terms together. That is, collect all the coefficient of x1, collect all the coefficient of x2. In torsional system it is theta 1 and theta 2. Then assume the solutions. What is the solution? This is a typical solution for every longitudinal problem. Small x1 is equal to capital X1 sin omega t and small x2 is equal to capital X2 sin omega t, where capital X1 and capital X2 represents amplitude of vibration of both the masses, and small x1 and small x2 represent motion at any time t. Then next step is take double differentiation of x1 and x2 so that you can put those values in your equation. Okay, then put the values of x1 double dot, x2 double dot in the equation of motion. Then cancel out the common term. Sin omega t is there in every term, so that you have to cancel. So remember friends, there will be no sin omega term in your final equation, because that is going to be cancelled out. Collect the terms of capital X1 and capital X2 together. Okay, means x1 term together, x2 term together, and then write two equations in the form of ratio of amplitudes, that is capital X1 upon capital X2. So you will be getting two equations like this. Then cross multiply these two equations, and finally you will get an equation in the following form. Which is that form? Ax square plus bx plus c is equal to 0. That means you will be getting the equation like this: omega fourth plus b upon a omega square plus c upon a is equal to 0. So this omega means it is a natural frequency omega n. Okay, here I have written omega, but this is because this is not no damping, no forcing force. Naturally, this is system will vibrate with natural frequency only. Next step is find out two values of omega n1 and omega n2 from this equation. Okay, these two values represent two natural frequencies of the said system, because this is a 2 DOF system. Next step is to determine the two mode shapes. Take any one equation of the ratio of capital X1 upon capital X2 and first put the value of omega n1 and determine the first principal mode shape. How, we will see in the problem. Again, consider the same equation of ratio x1 upon x2, put the value of omega n2 and determine second principal mode shape. Okay, and finally draw the diagrams of two mode shapes in proportionate scale. It is not to the scale, but it should be proportionate scale. Okay, so I hope you understood the procedure. Now let us go to the problem number 1. Okay, so the statement is, for the system shown in following figure, find out two natural frequencies for vibratory system. Also find out the principal mode shapes. This is a typical problem statement for every problem in unit number 3, that is 2 DOF system. Okay, the values of masses are given. M1 is equal to M2. Both the masses are equal. Okay, so that is equal to 9.8 kg. So after few say steps, M1 and M2, we are going to make it equal to M only. Okay, then there are 3 springs. See, 1, 2, 3. So the values are given. K1 is equal to K3. We are calling it as a K, that is common term, because those are equal. So that is given by 8,820 Newton per meter. And the middle spring, which is a coupled spring, intermediate spring, its value is given 3430 Newton per meter, and it is denoted by K2. Okay. Now let us understand this procedure. Okay. What was the first step I told you? You have to draw the free body diagram in displaced condition. That means here assume that M1 is displaced downward by x1 amount. M2 is displaced downward by x2 amount. Okay. So this is the original diagram, which is having 2 masses and which is having 3 springs. This middle spring role is very important. Okay. So draw the free body diagram of M1 first. What are the forces? See, as I told you earlier lecture also, no damping. So damping force is 0. No forcing function, external or unbalanced. So external force is also 0. So which are the 2 forces remaining? Inertia force and spring force. So the spring force acting by this first spring on this mass, as mass is moving down, this spring force will be upward and its magnitude is K1 into X1. Okay. Then inertia force, as it is going down, and I am going to apply Newton's second law of motion. So inertia force will be shown downward. What is the magnitude? M1 X1 double dot. Okay. Then this force we will talk a lot later on. Let us consider the M2 now. Here it should be M2. So what is the as this is going down, the third spring will exert the force in the upward direction. Okay. So this is that spring force. Magnitude is K3 into X2. This X2 and this K3. Okay. And the inertia force for this mass is M2 into X2 double dot, which is downward, because we are going to apply Newton's second law of motion. Now consider this, the force applied by this middle spring, intermediate spring. Here you have to apply your logic. Okay. See, first, why you have to assume that either X1 is greater than X2 or X2 is greater than X1. I told you, according to that, the direction of this force will be changing for M1 and M2. So here, what we have assumed, that X2 is greater than X1. Okay, this X2 means M2 is moving by more distance than M1. So first you have to show the spring force applied by this middle spring on this M2, as in your by applying your logic. So as this mass is moving down, this spring will be getting stretched. So force will be in the upward direction for this M2. So see here, we have shown it. What is the magnitude of the spring force? K2 into X2 minus X1. Here, this is very important step of why X2 minus X1, because this mass is moving down simultaneously. This mass is also moving down. So this is moving by X2 amount. This is moving by X1 amount. So what is the total deflection of the spring? X2 minus X1. So spring force direction is upward and magnitude is K2 into X2 minus X1 for this M2. And now for this M1, same magnitude is there and show it in the upward direction. Okay, so if, as this is upward, this is downward, because spring force will always exert equal and opposite. Okay, so when it is upward for M2, this is downward for M1. Okay, so remember here mass is moving down, but spring force is also downward. This is the difference. Okay, here students get confused. So understood? Now we have to apply Newton's second law of motion. Okay, so this is the given data M1, M2, etc. And what we are supposed to find out? Natural frequencies, that is omega n1 and omega n2, and then mode shapes, that is x1 and x2 for this is not for difference, so for your 2 values. Okay, now here so what is x1 and x2? I already explained you. This represent displacement of 2 masses m1 and m2 at any time at any instant measured from the equilibrium position. of the masses respectively, and we are considering downward direction as positive. Okay, so in order to write now the differential equations for these two masses, let us assume x2 is greater than x1. Okay, then draw the free body diagram of both the masses, show all the forces are acting on it, and now apply Newton's second law to both the masses. So what is it? Inertia force is equal to summation of all the forces. Here all the forces are acting in the actually vertical direction, but we are considering that is x only. In 2D wave system, we always consider x, whether it is horizontal direction or vertical direction. So summation fx is equal to 0. Now here always there is a pair equations in pair. Okay, so what is the first equation for this mass m1? Inertia force, which is acting downward. Okay, so here this is acting downward, so see here m1 x1 double dot, okay, is equal to, now there are two forces, k1 x1 upward, so negative, and k2 into x2 minus x1 downward, so positive. Okay, so this we have written here, m1 x1 double dot is equal to minus k1 x1 because acting upward, plus k2 into x2 minus x1 which is acting downward. Okay, similarly we have written for m2 also. So m2 x2 double dot is the inertia force is equal to spring force, this is upward, minus k2 into x2 minus x1, this is downward, plus k3 into x3. Okay, now from here 50% parts is almost mathematics, only mathematics, and that too very simple mathematics. We have to just go on simplifying the equation. Okay, so what we have to do here now, take everything on left hand side and equate it to 0. Okay, so that we have done. So m1 x1 double dot plus k1 plus k2 into x1 minus k2 x2 is equal to 0. Okay, then sorry, what we have done here, we have taken everything on left hand side. In addition to that, we have collected the term of x1 together and x2 together. Okay, so what are the coefficient of x1 here? Minus k1 and minus k2. Okay, so if you take x1 common, it will become k1 plus k2, and when you take on left hand side, it will become positive. So m1 x1 double dot plus k1 plus k2 into x1 minus k, there is only one coefficient of x2, that is plus k2 x2, it will become minus here, is equal to 0. Understood? Now for second equation, m2 x2 double dot, now coefficient of x1, see there is only one coefficient of x1, that is minus k2. Okay, sorry, minus minus plus, so when it will come here, it will become minus, so minus k2 x1 plus, now there will be two coefficient of x2, k3 and k2. Okay, so this is minus k2, this is plus k3. Okay, so I think some sign this minus x2, some sign confusion is there. Let me check. That I will find out later on, but it is plus, you remember this step is correct. So plus k2 plus k3, it should be minus here. Okay, so it should be k2 plus k3 into x2 is equal to 0. Okay, why minus? See here k3, I know where, see this one, this is upward, no, so this is negative. So here please make a correction, here it is negative. Okay, so that's why it will become positive and it will be coming on left hand side. So understood these two equations? We have just separated out collected the coefficient of x1 and x2 together. Okay, now we have to assume the solution. What is that solution? Say it is typical solution for all the problem for longitudinal vibration. So we have assumed assume the solution, small x1 is equal to capital X1 sine omega nt and small x2 is equal to capital X2 sine omega nt. Remember, very important here is that there is not omega n1 and omega n2. Okay, there is a proof in the mathematics that when your system will vibrate with the same harmonic motion, its natural frequency, each and every point of the system will vibrate with the same natural frequency. That's why for this solution, for mass m1 and mass m2, whenever it will be vibrating in principal mode of vibration, natural frequency will be same. That's why here also omega n, here also omega n. Understood? There is no omega n1 and omega n2 like coefficient 1 and 2. Now differentiate x1 dot here. So it will be capital X1 omega n cos omega nt. Okay, so here actually omega n is there. Okay, I have written omega n here. I have to write down omega n here. So cos omega nt, Then x2 dot is equal to x2 into omega n cos omega nt. Okay. Then x1 double dot is equal to, again differentiate, minus x1 omega n square into sine omega nt, and x2 double dot is equal to minus x2 omega n square into sine omega nt. Okay. Omega means here omega n only, because there is no external frequency. Okay. So where x1 capital, what are capital x1 and capital x2? These are the amplitudes of the two masses respectively, and omega n is the frequency of harmonic motion of both the masses. And as I told you, in mathematics there is a proof that two harmonic motions have to be of the same frequency. That's why there will be no omega n1 and omega n2, but there will be only omega n term. Okay. Now putting the values of x1 x2 and x1 double dot x2 double dot in the above equation. Which is that above equation? See these two equations, 1a and 1b. Here we are going to put the value of x1 double dot, x2 double dot, x1, x2, x1, x2. Okay. So see m1 into x1 double dot. What is x1 double dot? Minus capital x1 omega n1 omega n square sine omega nt plus k1 plus k2 into here small x1, that is capital x1 sine omega nt, minus k2 into small x2. So what is the value of small x2? x2 sine omega nt is equal to 0. What's the second equation? m2 into x2 double dot. So what is x2 double dot value? Minus capital x2 omega n square into sine omega nt, minus k2 into x1 into, what is the value? k2 into x1. So what's the value of x1? Capital x1 sine omega nt plus k2 plus k3 into small x2. What is the value of small x2? Capital x2 into sine omega nt is equal to 0. Okay. Now see, in every term there is a sine omega nt term. So this is going to be cancelled out because on the right hand side there is a 0. So cancelling out the common term sine omega nt. So what is remaining? Minus m1 capital x1 omega n square. From this one, see, minus m1 x1 omega n square plus in this term k1 plus k2 into x1 into this term minus k2 into x2 is equal to 0. Now in this equation what is remaining? Minus m2 x2 omega n square. In this one minus k2 into x1, and in this term k2 plus k3 into x2 is equal to 0. Okay. Now for simplification here we are going to assume whatever is given, m1 is equal to m2 is equal to m, and k1 is equal to k3 is equal to k basically. Okay, that we have to here I forgot to write down k here. Okay, so putting that value, simply I have written these equations again by putting m1 is equal to m2 is equal to m, and k1 is equal to k3 is equal to k. Okay, so minus m1 x1 omega n square plus here, so only we have replaced m1 and m2. Okay, and then here k1 plus k2, so it was k plus k2. Okay, k2 as it is here. Then here it is k2 into x1 as it is, but it is instead of k2 plus k3, it is k2 plus k. So there will be only one mass and two spring parameter k and k2. There will be no k3. Okay. Now collecting the coefficient of capital X1 and capital X2 together. Okay, see all now small x1 and small x2 are replaced by capital X1 and capital X2 because we have put the solutions. Okay, values of solution. So collect the terms of capital X1. See coefficient. See here, this is capital X1, this is capital X1. So we have collected together minus m omega n square plus k2 into bracket. Okay, that is X1, capital X1 is equal to this k2 x2 we have taken on right hand side. In this equation, coefficient of x2 and here also coefficient of x2 that we have collected together. Okay, is equal to, this is the coefficient of x1 that we have taken on right hand side. Okay, so what is our equation is in the form of something into capital X1 is equal to something into capital X2, something into capital X2 is equal to something into capital X1. Like this we got two equations. Now from this equation we have to write down the ratio of amplitudes, that is capital X1 capital X2. From this equation we have written, and again this equation we have written from second equation. Okay, so see from here capital X1 upon this capital X2, what is remaining on right hand side? K2 upon this coefficient we have brought as a denominator. Okay, then in this equation this x2 we have brought here, that is x1 upon x2. So this is the numerator. Okay, and denominator is k2. Understood? Now this is whether it is in this equation or this equation. The equation is given by capital X1 upon capital X2. So we must equate it. Okay, so here we have written capital X1 upon capital X2 is equal to this equation is equal to this equation. Okay, now as what is our aim? To find out the value of natural frequency omega n, because everything is known to us. K2 is known, K is known, M is known. Okay, only omega n is unknown. So now we have to solve this equation. This is only mathematics. Simple steps are there. Algebra. Okay, so cross multiply K2 into K2 square is equal to multiplication of these two cross term. Okay, see here these two terms. Now K2 square is equal to, just there will be A plus B into A plus B. Okay, so let us first term, there will be four terms. What's the first term? Minus m omega n square into minus m omega n square. This will become m square omega n raised to 4. Okay, then this term into this term, what it will be? Minus m omega n square into bracket K plus K2. Okay, then this term into this term, again minus m omega n square into K plus K2. Okay, plus this term into this term, that is K plus K2 bracket square. Understood? Then K2 square is equal to, you just add these two terms, these are similar, minus m omega n square into bracket K plus K2 and the same term. So it will become minus 2. Okay, so m square omega n raised to 4 minus 2m omega n square into bracket K plus K2 plus, now you expand it, A plus B bracket square. So it will be K2 square plus twice KK2 plus K square. Okay, so this K2 square and this K2 square will be cancelling out. So on right hand side it will be 0. Now what is remaining? M square omega n raised to 4 minus 2m omega n square into bracket K plus K2. Okay, this term, and then this is twice K square plus twice K into K2 is equal to 0. Okay, so this is your equation in the form of ax square plus bx plus c. Okay, so what is your A? See, m square is A, omega n raised to 4 minus, what is your B? 2mk plus K2 into omega n square plus, this is your C, K square plus twice K into K2 is equal to 0. Okay, so from this equation we are getting the two values of omega n square, because this equation is in quadratic in omega n square. Okay, which will give you two values of omega n. Okay, so one value is omega n1 and other value is omega n2. So this equation is known as a frequency equation because the roots of these equations are giving us two natural frequencies. Okay, so now first let us find out the natural frequencies. As I told you in the earlier lecture, that is also known as the eigenvalues. Now, what are the two roots of the systems? Omega n square and omega n2 square is equal to, here simply we have applied the formula of roots are equal to minus b plus or minus square root of b square minus 4ac upon 2a. Okay, so here see, already we have written the value. A is m square, b is this one, and c is this one. Okay, so that we have written here, b plus or minus b square minus 4 a into c, this is a, this is c, upon 2a square, 2a. Okay, now let us consider the first term. Take this 2m square here. Okay, then plus or minus, take this 2m square in the square root, that will become 4m raised to 4. Okay, now here we have expanded this k plus k2 bracket square. So it will be k square plus twice k k2 plus k2 square minus this term as it is. Okay, now in the next step, see here, these 2 will be cancelling out. M upon m square will become m, and what is remaining? K plus k2. So this will be k plus k2 upon m plus or minus square root of. Now see here, what is going to be cancelled out? 4, 4, 4. Okay, then m square, and this is m raised to 4. So what is remaining in the denominator? M square. Okay, now the terms will be, see, k square as it is plus twice k k2 as it is plus k2 square as it is minus this is k square minus 2k k2. Okay, now what are going to be cancelled out? See, this k square and k square, then twice k k2 minus twice k k2. So what is remaining? Only k2 square. Okay, so omega n1 square and omega n2 square, the roots are given by K plus K2 upon M plus or minus K2 square upon M square. Okay. So first root will be say minus, second root will be plus. Okay. Why? Because see, first natural frequency is always the lowest one. Always lowest one. That is known as a fundamental frequency. Fundamental natural frequency. Okay. So omega n1 square. Then you remove this. Now see, take the root of it is square root of K square upon M square. So that will become K2 plus M plus or minus. Okay. So omega n1 square. Take it minus. So it is K plus K2 upon M minus K2 upon M. So omega n1 square is equal to, so this plus K2 minus K2 will be cancelled. What is remaining? K upon M. Denominator will be same. So K upon M. That is omega n1 is equal to square root of K upon M. This is the simple natural frequency which we got for every problem in say unit number 1 for simple spring mass system. Okay, this is the first natural frequency. Now let us find out the second natural frequency. That means use the sign plus. So omega n2 square is equal to K plus K2 upon M plus K2 upon M. So this K2 plus K2 will become twice K2. Okay. So K plus twice K2 upon M. So omega n2 is equal to square root of K plus twice K2 upon M. So these are the two natural frequencies, omega n1 and omega n2. Those are known as the first natural frequency. This is second natural frequency. First natural frequency means it is always the lowest value. Okay, that is also known as a fundamental frequency. Okay. Now, putting what are the values of K, K2 and M are given, putting those values, we got the answer omega n1 is 30 radian per second and omega n2 is 40 radian per second. Understood? Now, the very important part, that is principal mode shapes. Okay, here that is also known as the eigenvectors. This part is somewhat difficult to understand the logic. Here now in this problem you will understand further 25%. As I told you, when I taught you theory in the earlier lecture, I told you that time you will understand the concept of mode shape hardly 25%. Now in this problem you will understand again next 25% or maybe 50%, and in every problem you will be getting this concept clear. Okay. So to find the mode shapes, we have to put values of two natural frequencies in any one of the equation of ratio of amplitudes. Okay. So which is our equation? C. K1 upon K2. This one. Here. There are two equations we have found out. X1 upon X2 is equal to something. X1 upon X2 is equal to something. Okay. So use any one of these equations because both are equal. And what you have to do? Put the value of omega n1 first. Whatever the values of x1 upon x2 you are getting, that is known as the first principal mode shape. Then you put second value of omega n2. And whatever you will be getting, the ratio of x1 and capital X1 upon capital X2, that will become your second principal mode of vibration. Understood? Now this procedure we are going to adopt. Okay. So let us go to mode shape. So this is our equation. So I am going to use this first equation. Capital X1 upon capital X2 is equal to K2 upon minus M omega square plus K plus K2. Here also simple mathematical terms are there. Simple algebra is there. Okay. So we have to put now first natural frequency. What is the value we have found out? Omega n1 is equal to square root of K upon M. So put here omega n square, that is K upon M. Okay. So we have put here K upon M. This M will be cancelling out. What is remaining? Minus K plus K2. See here we have written minus K plus K2. Okay, so this K and K will be cancelling out. What is remaining? K2 upon K2. Okay, so what is K2 upon K2? 1. So what did we get? Capital X1 upon capital X2 is equal to plus 1. Now this is known as a first principal mode of vibration. That's why we have written here first. The suffix is first. And we have to put this into bracket. Okay, this means that, what's the meaning of this one? The system is vibrating with the first natural frequency omega n1. The mode shape is such that the ratio of amplitude of two masses is equal to plus 1. The interpretation of this we are going to study at the end. Okay. Now, similarly, find out the second mode shape by putting the value of omega n2 into again either the same equation or you take any other second equation. Okay. So here put the value of omega n. What is the value of omega n2 here? We have found out second natural frequency square root of K plus twice K2 upon M. So put here value of omega n square. that is K plus twice K2 upon M. This M will be cancelling out. What is remaining? Minus K minus twice K2 plus K plus K2. See, we are written here. So minus K plus K will be cancelling out. Minus 2K2 plus K2 will become minus K2. And this K2 and this K2 will be cancelling out. So it will remain minus sign only. Okay. So what did we get? Capital X1 upon capital X2, second principal mode is equal to minus 1. What is the meaning of minus 1? Okay. That means when the system is vibrating with the second natural frequency omega n2, the mode shape is such that the ratio of the amplitude of the two masses is equal to minus 1. Now here we are going to interpret the mode shapes. Okay. What is the meaning of plus 1 and what is the meaning of minus 1? So listen carefully. This is very important concept. So first principal mode shape. What did we get? Capital X1 upon capital X2 is equal to plus 1. See, consider this diagram. Okay. This is your original system. M1, M2, K1, K2, K3. Okay. And then see how now you are in the first principal mode of vibration. What did we get? Capital X1, capital X1 upon capital X2 is plus 1. Means what? This mass has been given initial disturbance, initial amplitude, capital X1, suppose in the downward direction, and this mass M2 also has been given the initial displacement capital X2. Okay, here capital X1 upon capital X2 is equal to 1. Means what? If I push this mass by downward direction by 5 centimeter, second mass also I am pushing 5 centimeter in downward direction. Means I have taken capital X1 is equal to 5 centimeter, capital X2 is equal to suppose 5 centimeter, means equal. X1 is equal to X1, X2, and in the same direction. That's why plus sign is there. This one. Plus sign means that both the masses have been given initial displacement in the same direction. And you know that is only the amplitude. I have pulled this mass by 5 centimeter downward, M1, and also M2 also downward, and release. What will happen? The system will vibrate with the first natural frequency. Every point on the system will vibrate. See, I have written here. The ratio of amplitudes of two masses being plus 1 means the amplitudes of both the masses are equal, and the motion of two masses in phase, that means both are simultaneously moving downward, upward like this. That is, two masses move up and down together. Here, every point in the system executes harmonic motion of frequency omega n1. Each and every point in the system is vibrating with the natural frequency omega n1. Okay. This motion where every point in the system executes harmonic motion with the first natural frequency, it is called as a first principal mode shapes. Okay. Now in this, the role of intermediate spring K2 is very important. That is also known as a coupling spring, which is denoted by K2. Okay. You can imagine when these two masses are moving like this, upward and downward simultaneously with the same distance. What is the role of middle spring? It is neither going to stretch nor compressed during vibrations. It would simply move bodily with the masses and is therefore completely ineffective. You can imagine in between my two hands there is a coupled spring and I am moving like this bodily. The complete system is vibrating like this, up, down, up, down. See, the middle spring is not going to compress, not going to stretch also. So what is the role of middle spring? It is completely ineffective. So even if this coupling spring is removed, the two masses will continue as a vibrating. This is imagination, huh? And and that will become the single DOF system with natural frequency omega n1. This means the system can be mathematically modeled by two spring mass systems separately, as shown in figure B. And the natural frequency for these two systems would be square root of K upon M. Let us go to that diagram again. See here. First diagram is original system. Second diagram represent mathematical modeling of this one. Third diagram represent mode shape. This is your mode shape. We have called it as an amplitude plot. And this is the phase plot of two masses. Okay. Let us imagine now. The role of middle spring is 0, ineffective. So you remove this spring. What will happen? This will become your one single DOF system, spring and mass. This will become your other single DOF system, spring and mass. And you are familiar with this system. We are learning unit number 1, undamped vibrations. So what is the vibration of this system? Omega n1 is equal to simply square root of k upon m. Similarly here also. Okay. Now each and every point on the system will vibrate with natural frequency omega n1. Okay. So this mass is, what is the amplitude is maximum at this mass, that is 5 centimeter. As I told you, imagine 5 centimeter. And as you go up along this distance, the vibration, that is amplitude, will go on reducing, because this is a node point. What do you mean by node point? Means having zero deflection. It is not at all moving, steady. So this is a fixed point which is having zero amplitude. As you move away this distance, the amplitude will be increasing. It will be maximum at m, 5 centimeter. Okay. Then similarly for this one also, this second mass, it will be 5 centimeters suppose. Okay. And for as you go down, its amplitude will be decreasing and zero here. Okay. So this in between these two, this spring, okay, it will be again moving by 5 centimeter down and up without stretching and compressing. So this is 5 centimeter. Okay. Now this is the phase plot. See, for this mass, you can show it sinusoidally like this. And this is also for M2 mass. Both are in the phase. That means peak of this one matches with peak. Crest of this one matches with crest, like this. This is in phase amplitude, phase, you can say phase plot. Understood? First mode of vibration. Now let us go to the second principal mode of vibration. What did we get? Capital X1 or capital X2. Second mode, it should be second here, is equal to -1. What is the meaning of -1? The ratio of amplitudes of two masses being -1 means the amplitudes are equal. X1 is equal to X2. But two motions are out of phase. That is, one mass, if it is moving down, the other mass is moving up, but by the same distance, because capital X1 is equal to capital X2 and vice versa. Okay. Here, every point in the system executes harmonic motion with the frequency omega n2. Okay. So in this mode of vibrations, the intermediate spring K2 is symmetrically stretched and compressed alternately. Okay, this can be mathematically modeled by the system shown in figure D. We are going to that diagram. The middle point of the intermediate spring is neither stretched and nor compressed, only middle point of, not the whole spring, and does not have any motion and is effectively grounded, giving us equivalent system as shown in figure E. So such a point which does not have any motion is called as a node point of the system. Now let us have the look for this diagram. There are 5 diagrams total. Okay. So first diagram represent original system, same system. In the second diagram, see, this middle spring is, what is the role of middle spring? Now here, what type of initial displacement we have given? Say if M1 I have given 5 centimeter displacement amplitude, because that is the maximum displacement. So if M1 I am pushing down by 5 centimeter, M2 I am pushing upward by 5 centimeter only. Okay. So now these are two masses. So I have given the initial displacement like this and release. How the system will be vibrating? Like this. Up, down, up, down. Both are in the opposite direction. M1 and M2. This was not the case with the first mode shape. In the first mode shape, they used to vibrate like this. The whole system will be vibrating with this in the same direction, M1 and M2. But that is not the case here. In second principal mode shape, as we are given the initial displacement like this, either towards each other or away from each other, 5 centimeter. So how the system will be vibrating? Like this, in the opposite direction. Okay. So that is, so it is shown here. So what is the role of this midpoint of middle spring? See, the middle spring is compress, stretch, compress, stretch, compress, stretch. Okay. So what is the role of middle point? Okay, as it is compressed and stretching, it will remaining at its place only. It is not going to move at all. That is called as a node point. No motion is there. You can imagine, see this, you can relate it with the bending. If this is your bending of the beam, what is the role of neutral axis? Because see, upward layers are in the compression, lower layers are in extension, Okay, and as you go to the neutral axis, it is going to reduce or compression is increased. So there is a neutral axis which will remain neutral only, which is not going to compress also, which is not going to extend also. So similar is the case with this node point. Understood? So here as there is a zero amplitude because it is fixed point. Then here also zero amplitude because this is a node point. It is neither going to stretch nor going to extend. Okay. Now for M1, I have given 5 centimeter displacement. Okay, initially. So this is 5 centimeter, and as you go away from this one, it becomes it is decreasing. Okay, and again it is 0 point, so again it is decreasing in linear fashion. Okay, then again mass M2, I am moving in the opposite direction. Okay, that's why if this is on right hand side, this is on left hand side, in the opposite. That was not the case with the first mode shape, it was on the same side. Okay, so this is also 5 centimeter in the opposite direction of this one. Okay, again it is 0 displacement, here it is 0 displacement, so it will be go on reducing like this, like this. So this is the mode shape. It is known as the second principal mode shape. Understood? Now if we, this is a node point, okay, means it is a fixed point. So if you cut this spring into half, imagine, now this is the imagination, I can cut this spring in the middle only. Okay, and I can assume here the say support. So now this system, how it will become, there is a one spring having K stiffness, there is a other half spring having half stiffness, that is of K2. Stiffness will not remain K2 now, that we are going to see. So it will become two masses, two spring with single mass. And how these two springs are connected, whether it is in series or parallel, what do you think? Mass is in between the two springs. So these two springs are connected in parallel. Always remember, if the system is like this, spring and second spring, then these two springs are connected in the series. But whenever there is a in between mass is there, so this spring, then mass, this, then other spring. So these two springs are always connected in parallel. So what will be the you can say effective stiffness or resultant stiffness? Parallelly, how to add it in parallel case? K plus K2, simply K plus K2. Okay, that's why the natural frequency of this system will be square root of K plus K2 upon M. Did you now relate whatever we are getting? Same is the case for this system, K plus K2 upon M. Okay, so here it is. So resultant K is K plus twice K2, not K2. Why twice? I will explain you, because when you cut any spring in the middle, when you make two equal half of any spring, its stiffness will be doubled. Okay, this if you don't understand, please get it understood, because this is very important concept which you have already learned in theory of machine. So here it is shown, this is one system, this is second system. Okay, these are the node points. So we have converted two DOF system into two single DOF system. This is first system, this is second system, exactly similar. So this is mass M, so we have added these two. Okay, right now we have written here KH, H for half. It is half spring, so its spring stiffness will be different. It is doubled, I told you. Okay, so K is equal to K plus twice K2. Okay, then this is also K2 is equal to, this is also Ke is equal to K plus twice K2. Okay, so both the system will vibrate with the natural frequency omega N2 is equal to square root of K plus twice K2 upon M. What did we get in the natural frequency? And then this is the plot of phase plot. So see, this is a sinusoidal curve for M1 and this is for M2. So here see, as both the masses are moving up and down in the opposite direction. So here the crest of mass M1 matches with the peak of mass M1 matches with the crest of M2. Similarly, crest of mass M1 matches with the peak of mass M2, like this. Okay. So whatever we have found out, let us read. The amplitude on phase plot is shown in above figure. The intermediate spring can be divided into two equal parts in series. Okay. The stiffness of the each spring KH would be found as. Okay. So as these are, so actually this is opposite we are doing. Let us read this one. So the springs K and KH are in parallel. Okay, half spring KH and K are in parallel. Hence the equivalent stiffness is KE is equal to K plus KH. That is K plus twice K2. How this twice K2 has come, that I will read it. Hence the natural frequency of mode 2 is omega into is KE upon M. That is K is K plus twice K2 upon M. Okay. Thus the original system is now converted into two single DOF systems, each having the natural frequency omega N2. Now how this twice K2 has come, that is written here. See, you have to imagine now reverse thing. Imagine there is a one spring which I have cut it into half equal parts I have made. So if original spring is having the stiffness K2, okay, so it will be converted, the new spring, new half spring will be having the stiffness double. Why double? Because see, now imagine the reverse thing. This is half cut half spring, this is half spring which I have cut already. Now if I want to join it, these will be in series. Okay, I have cut the spring. Okay, now again I am going to join it. So these two are in series, KH and KH. Now what is the effective or resultant stiffness now? That is in series, no, connected. So that we have written here. 1 upon K2 is equal to 1 upon KH plus 1 upon KH, that is equal to 2 upon KH. So that means KH is equal to this twice K2. Understood? That's why this is the very important sentence, that whenever you cut the spring and make it two halves, the new stiffness of the new half spring will be doubled. So that is twice K2 instead of K2. Understood? Now let us go to conclusion of these today's lectures. Okay. So lastly, we can conclude that if there are three conclusions. First conclusion is, if the two masses are given equal initial displacement in the same direction and release, as I told you, 5 centimeter in same direction, they will vibrate in the first principal mode of vibration with the first natural frequency omega n1. And what is the value of omega n1? Square root of K upon M. Okay. But the second conclusion, if they are given equal initial displacement in the opposite directions, okay, that is 5 centimeter upward, 5 centimeter downward, and release, they will vibrate in the second principal mode of vibration with the second natural frequency omega n2. What is the value of omega n2? Square root of K plus twice K2 upon M. If however, now this is the third conclusion, if however the two masses are given unequal initial displacement in any direction, their motion will be superposition of two harmonic motions corresponding to two natural frequencies. This is your out of syllabus. This third case means what? M1 I have given 5 centimeter downward and M2 I have given suppose 7 centimeter upward. Means those are unequal in any direction. Then system will not vibrate with omega n1 or omega n2. It will vibrate with the combination of superposition of n1 and omega n2 value. Okay, that is the third case, that is not for your syllabus, and that is known as a simply mode of vibration. But these two, these are known as a principal mode of vibration. So what happens in principal mode shapes, principal mode of vibration, both the masses should be given equal displacement either in the same direction or in the opposite direction. Understood? Then the system will vibrate with the principal mode shapes. Okay, so let us stop here. Thank you very much. I hope you understood the topic.